All right, we're going to do the exam key for Friday's exam via Pencast so we can get a thorough overview for series in preparation for Tuesday's AP exam. So without further ado, let's look at question 1. What is the sum of this series? Round or find an answer to the nearest thousandth. Looking at it, you might tell, and I looked at this first here and here, because I see the k in both numerator and denominator, makes me think this is a geometric series because as k advances, some of the numerator and denominator will advance to the next k term, indicating that part of the numerator and denominator will be your common ratio. If it's ever a problem where you're not quite sure, you can never go wrong doing a k table, where k is the term position and a sub k is the term itself. Realize that, excuse me, series often use u sub k for series terms, but since the geometric series formula involve a instead of u, we can use a. Not a big deal, trust me. So when k is 1, a sub 1 is negative 2 over e squared. When k is 2, we have 4 over e cubed. When k is 3, and that should be enough to determine what the common multiplier is, the common ratio. So pulling out the information we need for the infinite sum of geometric series, we have a, or a sub 1, and that equals negative 2 over e squared. And as we look at each term from here to here, what was the common ratio, the multiplier, that took us from term 1 to term 2? And just a brief pause will let us see that the r value is negative 2 over e. Recalling that the infinite sum, now remember this s sub positive infinity is my notation. It's probably not a good idea. You could use general S for infinite sum. So I think I'm going to do this. This is what I would do for the exam, S, not this. That's just to help your understanding. Okay, so the formula is A, or A sub 1, however you prefer, 1 minus R. So I would just plug it in, simplify it. Negative 2 over E squared, all over, I don't know if it's necessary to have a larger compound fraction bar, 1 plus 2 over E. If you don't mind, I'm going to skip all the algebra mojo, and that takes us right to negative 2 over E parentheses E plus 2. That is fine. Unless the question says round final answer to the nearest thousandth on the AP exam, I'm always okay with a decimal answer or an expression answer. But if it says round it to the nearest thousandth, go ahead and round it. This one comes out to negative 0.156. If it does not say to round it, then you're free to leave it as just an expression. Question 2 wants us to look at the hypotheses of the integral test before question 3, which is go ahead and perform it. So do read carefully when you have questions involving the integral test. There probably are other convergence tests that have specific hypotheses, but the integral test seems to be the one with the most, so it might be fair game for a College Board question. In any case, the 3 hypotheses in a nutshell, which I did restate in every subpart, is that the function is continuous, the function, always positive, and that the function is strictly decreasing. And I mean, solve it like a calculus nerd, look at the derivative. All right, so part A, the function is continuous. So if we look at what we call the associated function, which is simply a variable swap from x to k, we have this, 1 over 2x plus 4, all to the 3 halves. You can simply see it that the only point of discontinuity would be when x equals, and you know what? As I'm looking at this, I realize I said x and I wrote in k. So let's fix that. So now we have 2x plus 4. So this function here is discontinuous at x equals, little algebra in my head, I have negative 4 divided by 2, I got negative 2. So then you would say f of x is undefined. Perhaps, you know what, I'm going to take that out and say discontinuous. You should be more specific. discontinuous at x equals -2, which is not a valid value for k, or something to that effect. Okay, done. So we're done. We showed the only point of discontinuity would be at an x value that is not part of k's domain. Okay? Second hypothesis of the integral test says that it's always positive. Wow, when you look at this, it's like there's really no work to do except simply articulate what it is. So always greater than 0 for all valid values of k. I guess that's it. I really can't think of anything more involved other than to almost restate that, duh, everybody knows that. Excuse me. So now we're looking at the strictly decreasing. Use the derivative on this one. We know what to do. So f of x equals 2x plus 4 to the 3/2, making f prime of x equal to 3/2, 2x plus 4 to the 1/2 times 2. Quick simplification on this one would give me 3 2x plus 4 all to the 1/2. You're free to use root form on that if you want. You could say also always greater than 0 for all valid values of k. I think that's it. Most of the quote-unquote work is really just articulating what appears to be an obvious conclusion, but just realizing that you brought it to mind, like, okay, discontinuity, always positive, and derivative. The work is not that complicated. What it really is showing that, yes, I addressed it, and articulating the proper conclusion. Now that we've shown that the integral test is appropriate in this situation, let's go ahead and perform it. So we convert the general term of the series into a function and put it into what is technically an improper integral. So 2x plus 4 to the -3/2 dx. And we know what we're going to do. We're going to convert this to limit L approaches positive infinity of the integral. 1 to L, 2x plus 4. Just proper notation. We never plug in positive infinity. We know that. U substitution should be obvious. 2x plus 4. And if you don't mind, I'm going to skip all the mojo and take us right down to 1/2 integral 6 to positive infinity. Oops, sorry, I just did what I said not to do. All right, L, U to the -3/2 du, and that whole thing is limit as L goes to positive infinity. Again, I'm going to skip all the plug and play. It should be pretty clear that that's going to equal 0. And again, articulating your proper conclusion, since I guess you should put the integral in. 1 to positive infinity, 2x plus 4 to the -3/2 dx exists. Remember, we do not care what the value is, just the fact that it exists. Since that exists, the series converges. Did not ask what it converged to, it just asked whether or not it converged. Happy face, properly articulated conclusion, life is good. And this one tells us to use the limit comparison test to determine whether or not that series converges. The limit comparison test is by far the easiest, most straightforward, happens to be my test of choice when I see something that looks like a rational polynomial. In fact, I'm not sure if it's the only one that would work, but it's definitely the one of choice. Remember that the shortcut is to use a known p-series. We know that there's a rule regarding the p-series, whether or not they converge or diverge based on the value of p. So you want to use a known p-series, which would be k approaches 1 to positive infinity, 1 over k to the p, where p is the difference. And I guess I could put in positive difference if you want. It should be obvious that you would use the positive difference, but just in case it's not, just pop that in, positive difference in degrees between numerator and denominator. Between numerator, I'm going to abbreviate, and denominator. So in this case, we know that if we were to multiply out the numerator and denominator, we get k squared plus blah, 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 over k cubed plus blah, 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 blah. I forgot to put there for over. So in this case, we will use, excuse me, series, okay, and I'm going to state the obvious, which we all know, which is known divergent. Now, in two places already on this slide, we had used the word known, and what we're talking about is whether or not the p-series that you pick is convergent or divergent. So you have to know when you pick the p-series if it's convergent or divergent. But the significance of that extends to if the limit exists, then both series behave the same. The given series that we have and the series that we chose, in this case the harmonic series. So if the limit exists, then they both behave the same. So when you pick one that you know converges, do the limit thing. If it exists, then the other one behaves the same, etc. So we'll be working with a known divergent series. Therefore, if the limit exists, we can extend that divergence to the given series. Excuse me. So the limit is just plug and play. So k goes to positive infinity, k squared plus 3k over, and I did multiply the numerator out, and if you don't mind, I would never ever do this on the AP exam. It's just to go k cubed plus blah, 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 blah. I'm not sure what I would do. I mean, if you're in the AP exam, would you multiply all that out? That's stupid. I would just leave it in factored form, knowing that it's a third degree when you multiply it out, but don't do this. Don't do the k cubed plus blah, 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 blah. Over 1 over k. I'm not sure if we talked about this a lot in class. Does it matter which series goes on the numerator and which one goes on the denominator? The answer is no, because if your limit exists as a rational number, it has to be strictly greater than 0. Therefore, the reciprocal will exist also. Yes, your limit value will be different, but the existence will not be affected by switching numerator with denominator. Then when you multiply by the reciprocal of the denominator here, in this case, so we're multiplying by k over 1 to the numerator, you can see why you use the difference in degrees, so that you get a match. It would simplify out, which I'm not going to do, to k cubed over k cubed plus all the blah, blah, blah. That limit is 1, therefore, since rho is between, since 0 rho, I know it looks like a p, goodness, plus infinity, strictly between, obviously, both series behave the same, making the given one divergent, or something to that effect. Given series divergent. All good. Again, this question tells you which test to use, but the form of the general term should also indicate that the ratio test is your best friend. Putting k factorial and k plus 1 factorial in a ratio is not a problem. We dealt with that last year on how to simplify it. So the factorial usually leads me to do the ratio test if it weren't already specified. Same with an exponent there. Obviously, we don't have a functional definition, so the integral test and limit comparison test are out. So we're told the ratio test anyway. As a reminder, we have the k plus first term and the kth term. The kth term is simply the general term as given to you in the series. So That's fine. And the k plus first term is simply a k plus 1 substitution in for k. So we have k plus 1 factorial over k plus 1 quantity cubed. The ratio test tells us to take the limit as k goes to positive infinity of the k plus first term over the kth term. Again, I don't know if swapping that would affect the answer, but I'm not going to mess with it. It tells us to put the k plus first term in the numerator. So let's do that. K plus 1 factorial, k plus 1 quantity cubed all over k factorial k cubed. So let's see what would happen when we throw algebra at this. Switch it out, so we get k cubed, k plus 1 factorial, k factorial, and then k plus 1 cubed on the denominator. You might remember how to simplify that from last year. This all comes out, leaving you just k plus 1. And the numerator, I got this k cubed blah, blah, blah thing happening again in the denominator. But I'm going to get k to the fourth plus k cubed over k cubed plus blah, 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 like that. Although what Pascal's triangle binomial expansion really isn't that different, or that difficult, excuse me, to do on that one. If you don't want to do this thing, which I don't think is a good idea, just leave it as k plus 1 cubed, realizing that it would be a third degree polynomial when multiplied out. And that equals positive infinity. We know that by the rational polynomial end behavior rule. And then just articulate your answer. Since limit equals positive infinity, this series diverges. Oops, don't forget your happy face. When looking for the radius and interval of convergence of a power series, remember that the radius is just the length of the interval plus or minus from the point of convergence, which is at x equals 3. So the radius is like just a positive integer value, like 1, 2, 3, something like that. But without overthinking it, the radius would be the length of the interval on one side, so it's plus or minus r, without taking into account the endpoints. I know that's about as vague as it gets. Like, well, let's say the radius is 3. Is that 3 all the way to the endpoint, or 3 infinitely close to the endpoint, not including the endpoint? So don't let your head explode over it. The radius is just what it would be if it went right to the endpoint. So the radius is just a positive integer value. We know that, and I would just bet money I don't have, that you're going to be asked for the interval, because then that forces you to take the endpoints into consideration, so you'll have the proper closed or opened notation / brackets on your interval. So the radius is not a reason to overthink it. The interval is where the real money is. We know in this case, when we have a power series, radius and interval of convergence, you're going to apply the ratio test for absolute convergence, And that one is very similar to the ratio test. It's it's the k plus first term over the kth term, limit as k goes to positive infinity. But your expression that you're limiting is all absolute valued. So it's quite a setup, and let's take a look at it in this case. So the limit as k goes to positive infinity, I would have x minus 3 to the n plus 1 over n plus 1 parentheses 2 to the n plus 1. And I'll just put a large compound fraction bar there. And then the kth term, which is just the general term as given to you. And that's x minus 3 to the k over k times 2 to the k plus 1. And as I look at this, I'm getting ready to throw algebra at it, I realize that I kind of switched my n's and k's. I'm not sure what you would like. Does not matter, does not matter, does not matter. I'm going to go with k because that's what I've been using. All right, got that. And then as said, it is a ratio test for absolute convergence, so it looks like that. Without putting all the algebra mojo on the slide, let me just get ready for the setup. You multiply by the reciprocal, the denominator, do your canceling, etc. But you are limiting as k goes to positive infinity. So what you want to do is separate out the x expression from the k expression. Since k is a positive integer, you can drop the absolute values on the k part of the limit, assuming there's nothing as it's written that would imply a negative term. So we have x minus 3 absolute value, and then you're going to get k over 2k plus 1. So again, because this term here, nothing indicates that you're ever going to get a negative term for a positive value of k. I know that says n, positive value of k. Then as you're doing your work, just drop the absolute value from your k group here. Now it will stay, the absolute value will stay on your x group. So your limit will typically come out to be an absolute value expression in terms of x, which it does. In this case, we're going to get, boom, we know that this limit here, I'll just use the green since it's already written, is 1/2. So that is part of your limit, 1/2, and then I have x minus 3 absolute value. All right, now notice there's no happy face around this box, so we're not done. I just boxed it so I could take it down here and I wouldn't forget any part of it. So now we're looking for the limit. So what x values make the limit comply with the convergence conclusion for the ratio test? And the ratio test concludes convergent when the limit is strictly less than 1. So now we got to do a little algebra mojo on this so we can get rid of the 1/2 and break out of the absolute value. So multiply through by 2. I still have this. Oops, I wrote a 1 in there. Hang on, so I'm just going to overwrite that to a 3. Less than 2, and then that's a algebra 1 conjunction. So we have this, 2, negative 2, no absolute value. So I made a conjunction out of it, add 3 to all sides, and I get 1x5. So this will tell us a little bit of the information that my point of convergence, my x sub 0 is 3, and since x extends from 1 to 5, I know that my radius is 3 plus or minus 2. So this tells me that my radius is 2, and that answers part of the question. In order to determine the interval with the proper inclusive and exclusive brackets, you have to look at the endpoints separately, and the endpoints go in the original series. So these are our endpoints over here. I'll circle them in light green, and we're going to check them in the original. So check, excuse me, x equals 1 in the original. So that goes up here, and equals 1, positive infinity. So 1 minus 3 would be negative 2 to the n over, oh, I keep writing n, I'm mixing up my negative 2 to the k over k 2 to the k. You might see that we could do a little bit of manipulation on this. K equals 1, positive infinity, it's a weird looking positive infinity. Pull out, this would be an oscillating factor, which would allow us to cancel the 2 to the k's now. And that would give us, or leave us, excuse me, just 1 over k. This should be clearly obvious as the alternating harmonic series, which is convergence. Again, convergent, excuse me. Again, I don't know if you have to say it's the alternating harmonic series, it's convergent. Not a bad idea, though. Which, oops, now I'm hooked on the k's now. Which is convergent because it's the alternating harmonic series. And then if I can squeeze in the corner here of the slide, we are going to check x equals 5. Plug that into the original, and we get what? 5 minus 3. I'm just doing that in my head. That's just going to leave you k equals 1 to positive infinity. The 2 to the k's are going to cancel out. And I'm going to be left with 1 over k, and then you could say which is divergent. Which is divergent. So my point of convergence is x sub 0 being 3. My radius is 2. Therefore, my interval, and I'll put it right up here, would be 1 to 5, excluding the 5, we just showed it, including the 1. So the answer components would be right here. Radius is 2, interval is 1 to 5. Now I get a happy face. And hopefully this one was as easy and straightforward and intuitive as it seems. You're going to use the Maclaurin series for sine x to generate the Maclaurin series for sine of 2x. Looking right at the problem itself as given, you're looking for sine of 2x in for sine of x. So it should be apparent that it is simply a u substitution, quote unquote, in the Maclaurin series for sine of x, putting in 2x for x. So sine of x is one of the biggies. So the Maclaurin series for sine of x is brain tattooed, right? Tell me, even if you're lying. It's brain tattooed, Mr. Torrey. X cubed over 3 factorial plus 5 minus, I think that should be enough, 7 factorial. So then substitute in. So substitute 2x in for x, and we got it. So sine 2x has a Maclaurin series, excuse me, of 2x minus 4x to the third over 3, not 3 factorial, plus 4x to the fifth over 15 minus 8x to the seventh over 315. So make sure you do your algebra and cut out some of the factors of the factorial that simplify out when you raise 2x to the third power or fifth power or seventh power. So make sure it's fully simplified. Life is good. Happy face. Similarly, this one tells us to take the Maclaurin series for sine x and do an algebraic manipulation, which is just multiplying it by itself, to form the Maclaurin series for sine squared. The only question, I guess, that comes to mind is, do you multiply these two? Let me just write them out and show you what I'm thinking. X to the third over 3 factorial times itself, x minus x to the third over 3 factorial, or the first 3 terms by the first 3 terms, which would be x minus x to the 3 factorial. Do you have it memorized? Should I pause? Plus, you know they go odds, right? So 5 factorial, the next one has to be x to the fifth. See how easy that was to memorize? I promise I'm not looking at it on another sheet of paper. X minus x to the third over 3 factorial plus x to the fifth over 5 factorial. Question mark. Which one do you multiply by? It might seem clear, like there's no question. I'll just multiply that, excuse me, because when I FOIL it out, I'll get 4 terms. The outer inners will combine, excuse me, just like old school Algebra 1, I'll have 3 terms and life is good. Problem, if you have 3 terms, you're going to want to make sure that you go out to the 5th degree. When you multiply this over here by this over here, you notice that there's no 0th degree term. So you're going to have to go out to the 6th degree term in order to get 3 terms. If you do only the one on the left, notated in green, then you're going to have only part of the 6th degree term. So as much as it's a pain, I might suggest overshooting what you think. That if it's 3 terms, you're like, okay, I'll multiply 2 by 2. Just overshoot it to make sure you get all the components of what will be the last degree term. So it's very interesting the way that one plays out. So I'm going to compound distribute the 3 by 3 that I have indicated in blue. So x minus x to the third over 3 factorial plus x to the fifth over 5 factorial, excuse me, times itself, plus x to the fifth over 5 factorial. And I hope we're all cool on what I mean by compound distribute, which means I'm going to distribute the x into all terms. Then when I'm done, I'm going to distribute the x cubed over 3 factorial into all terms. And last but not least, we'll bring in the x to the fifth to all terms that way. I think that's probably the best. You might multiply 3 by 3 in vertical format. I don't think I've ever done that. Anything that's correct is fine. So as we just start, it's a bulldoze. So x squared minus x to the fourth over 3 factorial plus x to the sixth over 5 factorial. That's the first yellow of the compound distribution. Minus x to the fourth over 3 factorial plus x to the sixth over 36 minus x to the eighth over 3 factorial times 5 factorial. I don't want to multiply that out yet. Plus x to the sixth over 5 factorial plus x to the eighth over 5 factorial times 3 factorial. So let me just double check that everything is good. I got that. I got that. Excuse me. And I got that. Yep, all good. Now you might notice already that I skipped this last distribution. Running out of colors. Let me find a different one. That this one right here into this one would have given me x to the 10th over 5 factorial times 5 factorial. There's no way I'm going to need that degree term. I already see that I'm going to get 3 non-zero terms, which again illustrates that this piece right here, which would be the x to the 6th, it looks like if you had only gone 2 by 2, you wouldn't have gotten all of your x to the 6th components, but I'm just doing that in my head. Oh well, continuing. X squared, and I'm just going to be like an old Algebra 1 student and do that. It's terrible notation, but I'm doing it anyway. My next degree is going to be my x to the fourth. It's right here, so these will combine to, what's the best way to write that now? Minus 2x to the fourth over 3 factorial, because that's a common denominator, so you're combining them over the common denominator. Next degree would be x to the sixth. Maybe I'll do that in green. So I got that, that, and that. I'm going to have to common denominator that, aren't I? Ew, old school arithmetic. So what's 5 factorial? That's 120. That's 36, that's 120. Common denominator is 360. So what is this? That's 3x to the 6 over 360. 6x to the 6 over 360. 10x to the 6 over 360. So plus 16x to the 6th over 360. And then we should clean that up just to make sure, equals x squared, can't do anything with that, minus 3 factorial, that's equal to 6, so I should get x to the fourth over 3, and then 16, 360, what's common to both of those would be 8, so plus 2x to the sixth over 45, and I'm calling that done. All right, happy face. Okay, this one's a little dicey, so listen up. I'll show you my approach. The voices in my head seem to like it, so hopefully you do too. I'm looking at the partial Taylor polynomial right here. And it's degree 100, which means this thing goes on and on and on, and I don't really care about the rest of it. The first 3 terms right here are going to give me a pattern, hopefully, to allow me to extract what happens right here. So remember that the general term for the Taylor polynomial, the general term is always the nth derivative of x sub 0, x minus x sub 0 to the nth degree over the quote-unquote matching factorial. So here I let d sub n equal the nth derivative of x sub 0. So I had something to work with that was more algebraic. So I had simple symbols and variables to work with rather than trying to duke this out looking at the form as it's written. So I'm looking at the second degree right here, and I know, according to the general term off to the right, that that should look like the second degree derivative times x minus 3 to the second over 2 factorial. That's sort of the general term without any simplification. That equals what I'm given, which is x minus 3 squared. And just so everything looks right, I'm going to put a 1 there and a 1 there. Now just pulling out what I need, d sub 2 over 2 factorial equals 1 over 1. D sub 2 equals 2 factorial. Therefore, the second derivative of 3 is equal to 2 factorial. Okay, not so fast. I'm not ready to conclude that the derivative is just the degree factorial that I'm at without looking at the other two given terms just to verify what's going on. So let's portion this off. Same idea. So let's look at the fourth degree term now. D sub 4, x minus 3 to the fourth over 4 factorial. That's the general Taylor term according to that form for this expansion. But that equals what's given to us, which is x minus 3 to the fourth. I'm going to put a 1 there for clarity, over 2 factorial. Pull off what I need. D over 4 factorial equals 1 over 2 factorial. D sub 4 equals 4 factorial over 2 factorial. And you'll see that I'm not simplifying them. When I simplify things out, I start to lose the pattern. At least that's how my brain works, or it doesn't work. So the fourth derivative of 3 equals 4 factorial over 2 factorial. And now I look over here and I'm like, I got a fraction over here on the right. I don't have a fraction over there on the left. So I'm going to make it a fraction just so it looks the same. Easy enough to put 1 factorial. Now I'm starting to see a pattern. One more to confirm, and I think you see it too. So d sub 6, x minus 3 to the sixth over 6 factorial equals what we're given, which is 1 x minus 3 to the sixth over 3 factorial d sub 6 is going to equal 6 factorial over 3 factorial, and I think I'm ready to draw a conclusion. So the 30th derivative of 3 would equal d sub 30 in our little notation thing that I made up. So following the pattern that I see is that the derivative value is equal to that order of the derivative factorial divided by half that order factorial. So second derivative, 2 factorial, half that. Fourth derivative, 4 factorial over 2 factorial, half that. Sixth derivative, 6 factorial over 3 factorial, half that. 30th derivative is 30 factorial over half that, 15 factorial, which equals 2.028 times 10 to the 20th. Nice intuitive problem. Happy face. All right, what's a series test without a little Lagrange error bound? So as we read this, we're doing a cold read, and we want the third degree Taylor polynomial. We want to approximate the maximum error for the third degree, which means, according to our notation, we have r sub 3 of x, which is going to be our notation for the remainder or the error using a third degree Taylor approximation. Well, remember from our formula that we are looking for the absolute value of that, and that has to be less than or equal to, and this is where I'm not sure what's the best way to notate it. I often use n plus 1, plus 1, and I got this nk problem, so I'm going to go with k just because I've been using that more this year. K plus 1. So it's k plus first derivative of z over n plus 1 factorial x minus x sub 0 to the k plus 1. All right, so and this really doesn't matter because it's a Maclaurin polynomial because we're doing that, no problem. The important part is to realize what this is saying. I'm really looking for the maximum value that this could take on. and realize that I should have absolute values here. Oh, that's a horrible looking one. Well, get over it. So I have this. I'm looking for the maximum value that this could take on. Well, I know that if this is a third degree polynomial and I'm looking for the error from it, this is going to be 3. There I go with my n's and k's now. It's driving me crazy. Crazy with a k. Get it? Okay. So k plus 1. So that's going to be 3. There's no question there. This is going to be the fourth derivative. So I guess I could just put 4 in parentheses, indicating that the k plus first derivative is going to be the fourth derivative in this case, and reminding us that z is an element of the interval 0 to 1. You're told that here. So it really is, what is the maximum value that the fourth derivative could take on in the interval 0 to 1, 0 being your point of convergence and 1 being the interval that you're given. So we're told that the fourth derivative is e to the sine x. We're told that. Well, it should be clear that the z value that maximizes the fourth derivative, z is going to be 1. It should be e to the sine x on 0 to 1, 0 to 1 radian. 1 radian is 57-ish degrees. That's first quadrant. Sine x is increasing. E to the sine x is increasing. It's strictly increasing on 0 to 1. That means the maximum value will be at z equals 1. So now, all of that discussion tells us this, that the remainder for the third degree Taylor approximation is less than or equal to the fourth derivative of 1 over, what's that going to be, 4 factorial. And don't forget that the z value is an x value, so this 1 is an x value in this interval, so it also goes right there. I just didn't want you to think I forgot it, because it really doesn't matter in this case, but it would be then 1 minus 0 to the fourth. So if you have different values that are a little more explicit, make sure you put them in, and we are absolute valuing this. So less than or equal to, calculator play, out to 4 decimals would give us 0.0967. And that is the Lagrange error bound. Your error is less than or equal to 0.0967. That's the 10th question. Tori out.